Hello, may I audible to you? Hello.
Yes, sir, you are audible.
Okay. Okay. We will wait for 1 or 2 more minutes for others to join. Then we will start. Okay.
Sure, sir.
Okay. Okay. Let's get started. So, welcome you all to the live session 3 on the course Manufacturing Processes Technology, first and second. So, here we will be solving some of the practice questions based on the video lectures of the week 4. So, let's get started with the first question. So, this is the first question. Uh, it is uh, it is from the casting process, and here we have to find out the solidification time. Please, first of all, try it by yourself, and then we will solve it together. And if you face any difficulty to understand the problem, I will please ask me. Hello,
Yes,
uh,
sir.
Hamid, can you please mute yourself? There is some noise. Hello. By reading the question, did you got some ideas how we are going to approach it, or still there is a difficulty? Make sure that there is a correction here. It should be degree Celsius, not zero. Okay. Okay, I think let's try to solve it together step by step. I would like your help. If you help me, then we will learn it together. Okay. So step by step, if we'll solve it, and then probably it will be easier to understand. Okay. So if you see what has been asked in this question, to determine time of solidification of the slab shape 15 centimeter thick casting. Okay. And the material is cast iron and it is poured with no superheat, okay, into a sand mold at the initial temperature of 28 degrees Celsius. Now we have been given with some of the data for the mold material as well as the casting material. So here uh, we have some slab whose thickness is 15 centimeter. This is 15 centimeter. Since other dimensions are not given, so we can assume that they are very, very large. It means this is the problem of thin slab or thin casting. So for thin casting, we know that length, this is the length, and this is the breadth or width, and this is the thickness. So length and breadth, they are very, very high than thickness T. So this is the similar condition, and now we will go we will learn how to solve this problem. Okay, so one more thing is given, that there is no superheat. It means pouring temperature, metal pouring temperature is similar as a freezing point of the casting. Okay, or we can say theta p is same as theta f. Okay, so let's try to solve it. Okay, so here we will find out what is the L dash, or the latent heat involved. Okay, so if you remember from the lecture, the L dash, the formula for L dash is this one, theta p minus theta f. So basically this term is for if we have some degree of superheat, then that these terms comes into the picture. But here, since we are given theta p is equal to theta f, so our L dash will be directly equals to the latent heat of the material for the casting. And if you remember what is given, if you can see here, that is given here 272 kilojoule per kg. And same time, what we can see that if you consider this slab, so uh, what would be the surface area of this slab? So it is somewhat cuboidal shape. Okay, so surface area will be equals to 2 times of length into breadth plus breadth into height plus length into h. Since we know that hello Rohit, can you mute yourself? Okay, since we know it is a thin section, so these terms, it will become 0, it will become 0, and finally we can approximate the total surface area of this casting will be 2 times of length time breadth, or these are the area, these are the major areas and opposite side of this face. Okay, and if we find out what is the volume of the casting, so volume is equals to length into breadth into height. Okay, and if you try to find out what is the ratio of the volume by surface area, so that is equals to V by A, and if we substitute these values, we will get L BH divided by 2 times of L into P, or that is equals to H by 2. And here, what is the thickness or H we have been given? That is 15 centimeter. Since H is equal to 15 centimeter, so H by 2 will be equals to 7.5 centimeter, or we can say V by A is equals to 7.5 centimeters. As well as, what is the temperature of the ambient? That is 28 degrees Celsius. So theta 0 is 28 degree centigrade. Now, in order to find out this time for solidification, we need to find out some parameters. If you remember from the lecture, there are some parameters like lambda and beta that is required in order to find out the uh, time required for the casting in the sand casting. So what was the lambda? Lambda is nothing but it is theta f minus theta ambient by theta f is what? It is the freezing point of the casting material or the casting metal. Okay, and theta 0 is the ambient temperature divided by density of the casting material or the metal times L dash, and this quantity should be multiplied by rho. Rho means what? Density of the sand mold. And C. C is what? It is the heat capacity of the sand mold. Okay, so let's try to find out what are the values given. What's the theta f? Theta f nothing. If you see here, that is the 1540 degrees Celsius. Okay, and theta 0 already, and theta ambient is already listed here. It is 28 degrees Celsius. So if we see the lambda, we know theta f, theta 0, and density of the casting material. So theta 0 is 28 degrees Celsius, and rho m, it is given 7850 kg per meter cube. It should be the meter cube. Sorry. And we have calculated L dash. L dash is similar to the L. L dash is similar to L. Why? Because there is no superheat given to the molten material. Okay, so L dash is equals to L, that is equals to 272 kilojoule per kg. So if we see the lambda, okay, now this is known, this is known, this is known, and L dash is also known, and rho is the density of the mold. And if we see what is given, density of mold is 1600 kg per meter cube. Okay, so we will note down rho is equals to 1600 kg per meter cube. And what is left? Heat capacity of the mold material. So C is the heat capacity of the molten material. So we will write C here. That is given 1 point here. C is equal to 1.17 kilojoule per kg Kelvin. 1.17 kilojoule per kg Kelvin. Okay. Okay. So now let's move to the next, and we will find out the value of the lambda. Okay. Okay. Please try to substitute the values and let me know the answer. Already I have shown the values of all the terms. Please substitute it and try to find out its value. You see, I have listed down all the values. Okay. If you have got the values, you can unmute yourself. Let me know, or you can write in the chat. Okay. Please keep on trying. Keep on doing calculation. Meanwhile, I will also write the values. Okay. If someone will get the value of the lambda, please let me know. Okay. You have to calculate this value. Okay. Okay, so what I'm doing, I'm writing the value, and later on you can verify it by yourself by yourself. Okay, so lambda is 1.325. Okay, now we have calculated the lambda value. Now, in order to find out solidification time, what was the formula? If you remember, okay, if you revise your lecture, you will find that we sir has taught that there is a relationship after recurrence derivation. We have got a relationship that is alpha time solidification time is equals to v by a to the whole square divided by beta square. Okay, so as of now, if you see, we have we have just calculated the v by a ratio, but we don't know beta. But beta depends the form basically the beta depends on the geometry of the casting. And in the course we have been taught two types of geometries, for spherical and for the thin slabs. And the formula for thin slabs which has been derived, it is beta is equals to 2 times of lambda divided by root over pi for thin slabs. Okay, so since already we have calculated the lambda, we will able to calculate the beta also. Okay, so here we will try to calculate beta. We will substitute the value and we will try to calculate beta. So beta is equals to 2 times multiplied by lambda. Lambda is 1.325 divided by root over 3.14, that is the value of pi, and the value of beta will come out to be 1.4957. Okay, now this is the relation we have with solidification time alpha and ratio of volume and area and beta. So only thing which is left to find out is alpha. Alpha is nothing, it is the thermal diffusivity of sand mold. Okay, alpha is the thermal diffusivity of sand mold, and that is given by K by rho C. What is K? K is the conductivity of the mold material. Okay? Mold material, and rho is the density of the mold material. And C is the specific heat capacity of the mold material. Okay, Now we will try to calculate alpha. So alpha is equals to k by rho c. If we substitute the values, we will get k. If you find in the problem here, k is given 0.8655. This is for the mold material. Okay, it is here. And if we try to find out rho, that is here, that is 1600 kg per meter cube. That is for the mold material. And the heat capacity is 1.17 kilojoule per kg. Now we will substitute these values to calculate alpha. All the values I am putting in the SI values. Okay, so if you calculate, you will find out the value of alpha is 0.46 to 10 to the power minus 6 meter square per second. Okay, now if you see the earlier equation here, alpha times solidification times is equals to V by A whole square divided by beta square. So by this relation, we will calculate the solidification time of the of our slab material. Okay, so now we will try to substitute the values of all the known things. So it will come out to be, this is the V by A ratio, this is the whole square of the V by A, and beta already we have calculated, will square it, and alpha already we have calculated, that is okay. And if you calculate it, you will find out time of solidification of our slab is, that is seconds. Okay, but if you see the problem, we have asked the solidification time in minutes, and if you calculate, if you convert it into the minute, then what we will do, ts in minutes, that will be equals to, it will approximately, it will come to the 91 minutes. Okay, so that is the answer. And which option it is? Yeah, third one. Okay, so this was the overall solution of the first problem. If any of you have any doubt, please ask me. Okay, since there is no doubt, so what we will do, we will move to the next problem. Okay, if the problem 2 is visible to all of you, hello, I am not getting any response. Any of you, can you please tell whether I am audible to all of you? Okay, thank you, Ami. Please read the problem too, and you can give your response in the chat box. Okay. Yes, Srinivas, you are correct. Others? Thank you, Ami. Yes, yes, both of you are correct. So let's try to discuss this for everyone. So if you have remember that there is a curve of there is a temperature curve that 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 shows that the what is how the temperature decreases from the molten metal to the ambient air. So again, I will draw that the same curve, and then we will try to find out the correct answer. Okay. Okay. On the y-axis, we will show the temperature, and on x-axis, we will show the different regions. Okay, so it is something like this. This is the region of the mold wall. Okay, and this is the air, and here we have solidified metal. And after solidified metal, what will come? Liquid metal. So what is this? What is this hatch region? Okay, let's make it a little more simple. Suppose we have a cavity something like this. Okay, this is the cavity, and it is made up of, basically there is a sand around the cavity, and outside there is air. Air. This is air. So whatever we have plotted, that is the temperature profile from center, let's say center of the mold, to the here. Okay, if you remember, when we pour the liquid metal inside the mold, it will get filled inside the mold, and solidification process will start. And from where solidification process starts, it takes place near the mold walls, because the molten metal which comes in the contact of the mold wall is solidified earlier because the heat transfer happens quickly. So something like that. So the dark red hashed region is the solidified metal, whereas the center there is a liquid metal. So center there is a liquid metal, that is this zone which I am showing, and the red hashed region which I am showing schematically, that is the solidified metal which is stick to the mold wall, that is this region. It is here, and the region which is for the mold wall, that which is this is the whole thickness of the mold wall, and that region is here, and outside of the mold wall this is the air which is shown here. So the temperature will be maximum at the in the region where metal is in molten condition. So those ranges are this, that is this region. Okay, that here the temperature will be the maximum. After that, what will come? This interface. This is the interface of solidified metal and molten metal. And here and here, this region is the interface of solidified metal and mold metal. And mold. Okay, now if we see the temperature profile, so it is maximum in the molten material. Okay, and at the interface of the molten metal and solidified metal, the temperature is little bit smaller, that is theta f, or the freezing temperature of the material. But as soon as if we come near to the mold wall, there is a peak drop of the temperature. Okay, this drop of material happens at the metal mold interface, and that happens because there is some formation of interlayer takes place, or there is a, if you go to the micron level, then there is a gap, or there is a region where the contact has not taken place correctly, or there is a gap between the solidified metal and mold material. Because of that, there is a big drop of temperature takes place just near the vicinity of the solidified metal. So if we see the problem, what has been asked, which of the following region in casting shows linear or steep decrease in temperature? So this is the overall region temperature profile of the casting process. If we see the sudden drop that is happening here at the interface of solidified metal and mold. So the correct answer for this problem is this one. Okay. So still, if any of you have doubt, please ask me, or we shall move to the next problem. Okay, seems it is clear to everyone, so we will quickly move to the next problem. This is also a problem similar kind of the first one, but here we are not take the our casting is not in the slab form, it is in the spherical form. So uh, please take some time to understand the problem, and please let me know if you find any difficulty to understand. And any of you can tell me what is the difference between how, where, in which process uh, we will find the difference during the time of during the solidification time calculation in comparison to the one. The steps will be very similar to the first problem, but there will be a change in certain step. So please let me know where that kind of step, in which step we have to do modification. Okay, please read it and take some time. Okay, let me help you out. So if you want to find out what is the time which is required for solidification of the casting, so what we did first we calculated L dash. If you remember the first problem, first of all we calculated the L dash, then we calculated the lambda. Okay, and after that we calculated beta, and also we have calculated V by A, and finally we calculated thermal diffusivity of the mold or alpha, and finally we used a relation that was something like this: alpha time solidification time is equals to V by A to the whole square divided by beta square. Okay, so where the change will come? Earlier we had thin slab, now we have spherical casting. So in which value you think difference will occur? Any of you? You can write in the chat or you can unmute yourself. You can please let me know which parameter will change by changing the geometry. Okay, okay. So let me help you out. So beta, Hamid, actually here we are solving for the spherical problem. So, uh, yes, if you are telling height, so height itself it not here we are not using height independently anywhere. Earlier, what we had a slab like this. It has some thickness we denoted by h. That was earlier it was 15. Now we are going to make a spherical casting. Okay, and now the diameter is 15 centimeter. Okay, so geometry has changed, but because of change of geometry, which factor is affecting? That is beta. So okay, uh, let's try to solve it together by step. Okay, so first of all, again we will calculate this. Yes, I mean apart from the geometry, other things are same. Here, please make sure that here it is sphere. Okay, let's try to solve it together. First of all, we will calculate L dash. L dash is equals to L plus Cm theta p plus theta f. Theta p is what? It's the temperature, pouring temperature, and theta f is freezing temperature of the mold material, and L is the latent heat of the mold material. So if you see the data, the theta p is again 28. Sorry, pouring temperature is given. It is poured with no superheat. It means theta p is equals to theta f. No superheat means pouring temperature is same as freezing temperature. No superheat. So if theta p is equal to theta f, this term will become 0. So theta p will also becomes to the theta f, that is equals to 1540 degrees centigrade, and this term will become 0. The finally we will left with L dash is equals to L, and what is the L? L is given 272 kilojoule per kg. And next step is to calculate lambda. So what was the lambda? Lambda was freezing temperature minus ambient temperature divided by density of the metal times L dash multiplied by density of the mold metal, casting material, and heat capacity of the mold material. So this is the again mold, and this is the heat capacity of mold. And again we will put the values. into 1600 times 1.17 into 10 to the power 3 divided by 7850 into 272. It is given in kilojoule. We will convert it into joules, and the value we will get is 1.325. It is same as earlier. This lambda value is not get affected by changing the geometry. But what is the beta for the spherical material? Beta for sphere, spherical geometry. So that will become lambda times beta is equals to lambda times 2 by pi, 2 by root over pi plus 1 times 1 by 3 times of beta. Okay, so this is the relation for sphere. Okay, so we can see there is a relation between the lambda and beta for the sphere that is given by this equation. Now we will substitute the values. We'll get beta is equals to 1.4957 plus 0.4419 times of divided by beta. What we can see, it is nothing but a quadratic equation. So again, if we simplify it, what we will get a quadratic equation, which is beta square minus 1.4957 times of beta minus 0.4419 is equals to 0. So we will solve it for the beta, and we will try to find out what are the real values of the beta. We will take only positive real values of beta, that is given by beta is equals to minus p plus minus. This relation uh, you might be knowing already from your 70th class mathematics. So if you use this relation and to trying to find out the values of this of the beta, what you will get, beta is equals to 1.75. I'm sure that you will be understanding what is the b, what is the a, what is the c in order to solve the quadratic equation. So that I'm not telling. So you will, if you solve this quadratic equation, you will find out beta is equals to 1.75. Now what is left? We have to find out the volume by area, surface area ratio for the sphere. So for sphere, we and diameter is the diameter is given 15 centimeter. So radius will become 7.5 centimeters. If we calculate the volume, if we calculate the ratio of the volume and area, it will become 4 by 3 4 by 3 pi r cube divided by 4 pi r square. Okay, so this is the volume of the sphere, and denominator is the surface area of the sphere. Okay, 4 by 3 pi r cube is the volume and 4 pi r square is the surface area. And if you solve it, we will get it r by 3. Now we will substitute the value of r. We will get the v by a ratio as 7.5 into 10 to the power minus 2. Now I am converting it into meters. Okay, this is the volume by area ratio. Sorry, it will be meter. Okay, what else we are left with? We need to calculate alpha, and alpha will be the same because it doesn't depend on the geometry. Alpha is the thermal diffusivity of the mold material. So that will be again k by rho c. If you substitute the values, it will come 655 1.17 to 10 to the power 3. If you calculate it again, you will find alpha. It is same as the previous first problem, that is 0.46 into 10 to the power minus 6 meter square per second. And now we have to put all the values in the relation. Alpha times solidification times equals to v by a to the whole square divided by beta square, or ts is equals to v by a whole square divided by beta square into alpha. And if we substitute all the values, what we will get? Ts equals to 443.6 seconds, or if we convert it into the minutes, it will come near about 7.3 minutes. So the correct answer for this problem will be, we can see this one. Second one is the correct answer because it is close to the 7.3 minutes. So I have explained the problem number 3, which is very similar to the problem number 1, but still if any of you have any doubt, please let me know. If you have any confusion in any step, please let me know. Okay. Okay, if there is no doubt, we will quickly move to the next problem. Even later on, if you find some difficulty, you can ask me. Okay. Please read the problem, and you can give your response in the chat box. After that, we will solve it together. Sorry, here in the building, we should have casting. Yes, yes, Naga, you are correct. Okay, okay, now let's try to see together that already we have shown that temperature profile of typical casting. So again, I will draw the same diagram, something like this. So we have temperature, and here we have different regions. So this is the mold region, mold wall. This is the air, and here after the mold walls, there will be some region where the molten metal has been solidified. And after that, we will have a zone with liquid metal, and we know liquid metal has highest temperature. So if we see this region, so what is this? It is the interface interface of solidified metal and mold wall. Okay, so, so we know there are different kinds of mold we have, like we have sand mold, or we have some metallic mold in the permanent mold casting, or the die casting. So in the case of uh, in the case of metallic mold, what happens when material solidifies? When material starts solidifying near the mold walls, then the material which is very close to the mold wall, they got stick to the mold wall. Okay, so I will show it by schematically. So first of all, we will have a mold. Okay, this is, let's say, metal mold, and it is filled with the molten metal. Since the mold is made up of metal, so it is it has good conductivity. So what it will start? It will quickly it will start extracting the heat from the molten material. So heat is coming out from the molten metal to the mold wall, and this is very fast process because of the good conductivity of the metal mold. So something like this. So metals very close to the mold wall starts solidifying. Okay, so what is happening here? In the center we have molten metal which has highest temperature, and outside we have air which is at, let's say, 25 degrees Celsius. This is air. Okay, air is at 25 degrees Celsius, whereas molten metal, it is at above. If we talk about cast iron, so let's say it has 540 degrees Celsius. because of temperature difference, what will happen? Heat flux will takes place. So heat will start flowing from the molten material to the ambient. So like this. So all the way. So heat, if you can remember, heat flux is very similar to the electric current. So what happens when electric current, if we have some conductor and electric current passes through it, it means potential drop is taking place. Similarly here, if we have heat current or the heat flux, if it is moving via conduction, then definitely temperature drop would have been taking place. Or we can say positively, if we have a temperature difference similar to as potential difference, if we have temperature difference, then electric then heat flux will takes place from high region to from high temperature to low temperature. Here high temperature is the molten metal, low temperature is the air. And when heat flux will move, it will face some resistance in between. So so when heat will start from the center, it will move within the liquid, and that is driven by the conductivity of the liquid material. After that, some molten metal has solidified. It will face different resistance within the solidified metal. After that, there, there will be a region between the solidified metal and mold wall, which is here. If you closely see, there will be a little gap. If you closely see, if the wettability of the both metal, if the wettability of the molten metal with the mold wall is very good, then this contact is very good. Okay, so suppose this is the molten, this is the mold wall, and we have molten metal which has very good wettability, and that depends on its surface tension properties. If the it has very good wettability with this metal, then we will have a very good contact. So there is a material continuity. So when heat flux will move from the molten metal towards the ambient, then it won't find much resistance at the interface because there is a metal continuity is there. But suppose the mold if the molten metal if the molten metal uh, have doesn't have good wetting properties with the mold, then how it will look like? So it will look like something like that. This is the mold wall. There will be some gap, and there is a minor air pocket in between the solidified metal and the mold wall. So this is the gap region. So if this gas gap will be there, and when heat flux will try to move from the center to the ambient, then here in the gap region we would have air. It will find large big heat resistance. We know air is the poor conductor of the heat. It means the resistance of air is high. So in this region we will find very high resistance of heat, which will cause difficulty to extract the heat from the molten metal to ambient. So it will slows down the solidification process. So if we now we will come to the question, the condition of no contact resistance. No contact resistance means there is a very good wettability, there is a uh, continuity of metal. If continuity of metal is there, no contact, there will be no resistance at the contact, and that condition is called no contact resistance. And because of when no contact resistance will takes place, if casting casting gets soldered or adhered to the mold face, okay, if there is a good wettability, good soldering, then there will be good adhesion between the mold material and the casting material, so good soldering will happen and no contact resistance will take place. So the correct answer is B. Okay, is it clear to everyone? Any of you have any doubt? Okay, so it seems there is no doubt. We will move to the next problem. Please read the problem and try to solve it by yourself. You can give your response in the chat box, then we will together try to discuss it. If you have any difficulty to understand the problem, please let me know. I will explain it. And if you have understood the problem, then you can give your response in the chat box. Any of you? Till now, I haven't received any response in the chat box. Okay, so let's try to see it together. So it has been asked, in what way metal mold varies from the sand mold while undergoing solidification. Okay, so so let's try to draw the schematics. So first we will draw for the sand mold. So our mold is made up of sand. And next we will draw a mold which is made up of metal. Oh, sorry. It is solid metal. Now we will fill this with molten metal. And here also we will fill the mold with the molten metal. So what is the basic difference? This is the sand mold, this is the metal mold. So with respect to solidification, what are the fundamental differences? So one thing is it is made up of sand, and here it is made up of metal. And we know metals are very good conductor. So metal means good conductor. Whereas the sand, even if you see the sand mold, it is sand is made up of some silica, and even within the silica particles there are air pockets and there are inorganic materials, additive materials, clay is there. So, or we can say it is a poor conductor. Okay, so sand mold are poor conductor, whereas the metals molds are good conductor. And since metal is a good conductor, so it will extract the heat very quickly. Okay, so whereas the sand mold, it will not extract the heat very quickly, so the heat transfer rate will be very slow. So what will happen here, solidification process will be the faster. So here material will solidify faster near the mold walls. Whereas the in the sand mold, the material will be solidify little bit more uniformly throughout the region. So if you see the whole region, since the heat transfer rate is very slow, so the cooling rate will be very slow. Therefore, therefore solidification will process be little bit more uniform in comparison to the metal mold. In the metal mold, since the it has good conductivity, so their directional solidification takes place very quickly. So quickly metals start solidifying from the mold wall towards the center, whereas it will not take place in the sand mold. And here, since heat transfer heat transfer is very highly dependent upon the conductivity of the material which are coming in the way of the heat. So here heat is moving from center to the ambient. and heat transfer is highly it is highly sensitive to the resistance or the uh, thermal resistance or the thermal conductance of the material. So since the solidification have started from the mold wall very quickly, so when heat will start traveling from the molten region to the ambient, it will encounter the solidified material. So it will heat will starts moving from here, and what it will find this region, the region of solidified metal. Whereas this kind of process will not take place in the sand mold. So here the heat transfer rate is already very slow in the case of the sand mold. So that there the solidification will not get much affected by the uh, resistance of the solidified material. Whereas here it is highly affected by the solidified metal. So if solidified metal will have good conductivity, then our whole casting will get solidified quickly and uniformly. But if the solidified metal will not have the good conductivity, then even if our mold is very good conductor, the heat transfer will not takes place. So if the solidified metal will not be good conductor, so whatever how much good conductor uh, how much good conducting mold material we will take, it will not, the solidification process will become slower. Or we can say the effect of solidified metal is very dominant in the case of in the case of solidification in the metal mold, whereas the its role is very negligible in the case of sand mold. So if we now if we try to see what are the options we have given, then the thermal conductivity of solidified metal, yes, C. So it is the biggest uh, it is the biggest difference we can find out in the case of the mold metal, uh, sorry, metallic mold and sand mold with respect to solidification. Okay, if there is any doubt, please let me know. Is it clear to everyone? Why the C will be the correct answer for this question? Any of you have doubt, please let me know. If it is clear, so we will move to the next problem. Okay, it seems there is no doubt. Just remember that in case of metal molds, the material which is solidifying, it plays its thermal conductivity plays a big role in the process of the solidification. So let's quickly move to the next problem. Problem number 6. Please read the question and try to give your response in the chat section. Yes, Srinivas, I have got response from you. Okay, anyone else? Yeah, I am looking for response from others also. Okay, I have got couple of responses. Okay, let's try to solve it together. So, uh, first of all, again, we will quickly draw a schematic of the solid casting process. So it is something like this. This is screw, and somewhere we will have something called riser. Okay, something like this. So here we have something. This is the mold, and we try to fill this mold with the molten material from the sprue, and this is the riser. So what will happen? We will fill the mold with the molten metal, and as soon as the molten metal will get filled, completely filled inside the cavity, this is the cavity, then extra material, we still pour some extra material, and that material comes out from the riser, and from here we will come to know, yes, our mold has been completely filled. So one thing riser has absorbed, that it is an indicator of, yes, our mold cavity has been filled. But apart from it, it has another job. And what is that job? We know whenever the molten metal solidified, its volume gets shrinked. Okay, so the molten metal in the cavity region, when it gets solidified, then its volume gets shrinked. So if during that time, whatever the volume shrinkage has been taking place, if that much of extra material, if we will not provide, then the our casting size will be smaller than the desired one. In order to avoid that, we provide a riser, and job of the riser is to supply the required molten material during the solidification shrinkage. So the riser will keep on providing the molten material. It will be same amount of molten material which is needed to overcome the shrinkage during the solidification inside the cavity. So so what we have to take care, one thing we have to take care, that the molten metal from the riser to cavity, it can come inside only when the metal inside the riser will remain in molten state. So even if our material inside the cavity has been solidified, but the material inside the riser should not get solidified. Okay, so if we want to avoid the, or if we want to delay the solidification of the molten metal inside the riser, what we can do? So then what we have to do? We have to reduce the heat transfer rate. Okay. So if the heat transfer from the riser region is slower than the heat transfer from the cavity region, so in the cavity region heat transfer will takes place everywhere towards the mold wall, like here. Okay, here wherever the molten metal is coming in the contact of the area of the mold, from there the heat is going away to the ambient. Similarly, if you see in the riser, the heat is going away from the everywhere wherever the molten metal is coming in the contact of the mold walls. So what we want solidification in this riser happens slowly, so that it could able to provide the molten metal to the uh, cavity, to the metal cavity during the solidification. A- and that heat transfer is totally depend upon the area of the contact. Okay, so suppose we have same amount of molten metal. Let's say we have one bucket of molten metal. Okay, if we have one bucket of molten metal, if it is inside the bucket, then the surface area which comes in the contact of the molten metal is this much. Okay, but what will happen if we pour the molten metal on some flat surface? So all the molten metal, if I poured on some, let's say, flat surface, okay, what will happen? It will cool down quickly. So what we can say, the solidification time is uh, some proportional, it is proportional to the area. Okay, so same amount of material if we have, if it comes into the larger contact area, then it will solidify quickly. Whereas if we have less material, or if we have, solidification time also depends on the volume. So if we have more volume, it means we have more amount of molten metal, more amount of heat. So if we have more volume, then we will be having more amount of heat. So the solidification time will takes longer time. So solidification time is inversely proportional to the volume. So this is the this kind of relationship we can think of, that if area is greater, then solidification is faster. If volume of material is greater, then the solidification will be slower. So what, or indirectly what we can say, solidification time or we can say, sorry, this is, or we can say solidification time, it is larger if we have smaller area, or it is inversely proportional. Whereas solidification time is larger if we have larger volume. So if we take the ratio V by A, this 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 ratio should be the larger if we want to increase the solidification time, and vice versa. So if we want to riser to solidify later, then what we will do? by this relationship, again we will try to reduce the area and we will try to increase the volume. Okay, so which is the correct answer? If we want to in- increase the solidification time of riser, then we have to reduce the surface area and we have to increase the volume of riser. So that is the correct answer is this. This is the chosen the minimum A by V ratio. Okay, so we have to minimize the area, we have to increase the volume. So that is the correct option. If any of you have doubt, can you please let me know? Hello, is it clear to everyone? Hello. Okay, okay, okay. If it is clear to everyone, so let's move to the next problem. Yes, please read the problem and you can try to solve it by yourself first, or you can tell me what will be the approach, and then we will together try to solve it. Any of you have any confusion in order to understand the problem? Please let me know. And if you any of you have got any idea like how we will solve it or what should be the approach, you can also unmute yourself. You can let me know. Fundamental concept is the same like in whatever we have discussed in the earlier problem. Like we want to reduce the solidification time for the riser, so that will be the key for the for this problem. If anyone of you have got uh, if you, anyone of you have got how to reach this problem or how can solve it, any idea, you can discuss with me. Okay, so let me help you out. So if we see what is given in the problem. Determine the dimensions of a cylindrical riser to be used for casting an aluminum cube of 20 centimeter. And what is given? Volume shrinkage of aluminum during solidification is 6.5 percentage. So it is saying that we want to cast a aluminum cubic block. Okay, so let's draw it. Okay, so this is the aluminum cubic block, and its size dimensions are 20 centimeter by 20 centimeter, and width is also 20 centimeter. Okay, so this is the final product we want. So what we will do, so the what we will do, make we will make a mold, make a mold cavity of same dimension. Okay, so let's make it. So here we have mold. Wait, here we have mold cavity of cuboid shape, and something like this. This is the sprue. Yes, this is the sprue, and here what we will make? We will make a riser. Something like that. Okay, so this is cylindrical riser. Okay, so these are the mold region, and this is the riser. And not what I am doing, I am filling this mold with molten material. Molten material is coming inside the mold, as well as it is also filling the riser. Okay, when mold is completely filled, as well as the riser metal will start coming out from the riser, we will stop the pouring, and we will left the casting for the solidification. After some time, what will happen? uh, some of the metal will start getting solidified. So we have made a mold of 20 centimeter cross 20 centimeter cross 20 centimeter. Okay, so when volume shrinkage will takes place, then our casting size will reduce, and that metal will get filled inside the molten metal from the riser should come here, and it will compensate the shrinkage. So that is the key idea that we have to do. But let's try to calculate how much volume we have and how much volume is required after the solidification. So the volume of casting is, that is V is equal to 20 cross 20, that is 8000 centimeter cube. And if we calculate the surface area of the casting, it is, that is 6 times of the area of a single face, that comes out to be 2400 centimeters square. Okay, and how much volume of metal is required after the solidification, that has to come from the riser, that we will calculate by uh, we calculate from the shrinkage, from this volume shrinkage percentage. So the shrinkage volume is, it is 1000 into 6.5 on 100, that comes up to be 520 centimeter cube. So this much volume of material we needed, and that should get supplied from a cylindrical shaped riser. Okay, now we don't know what is the height of the cylinder and what is the diameter of the cylinder or the riser. So let the height of riser is h and its diameter is d. Okay, so now we will try to calculate what is the area of, what is the total surface area of this cylindrical riser. Okay, so this is area of riser, that comes out to be pi dh plus 2 times of pi by 4 d square. Okay, so this is the typical full complete or total surface area of a cylinder. And same time, if we calculate what is the volume of the riser, so for simplicity I am using just a and v for a, for the area of riser and the volume of the riser. So volume of riser will be pi by 4 d square h, or area of the cylinder, area of the base of the cylinder times height of the cylinder. Okay, and if you want to draw a relationship between height and the volume of this from here, if you want to try out, if you want to substitute value of h in the terms of volume, what we can say, h is equals to 4 times of volume of riser divided by pi d square. And now this h value we will substitute here. Okay, so now our area can be written as pi d 4 times of volume of riser divided by pi d square. Now this is the value of h we have substituted as 2 pi d square by 4. So what here we are doing, we are designing the riser, and we know shape is cylindrical shape, but we have to find out, but we are trying to find out what should be the relation of height of the cylinder and diameter of the cylinder. And we know if we want to riser to solidify later, or if we want to solidification time for the riser to be the maximum, then what we have to do, we have to minimize the surface area of the cylinder. Already we have calculated that the shrinkage volume is 520 centimeter cube. So the volume of the riser should be the 520 centimeter cube. But for that 520 centimeter cube, there are n number of cylindrical dimensions are possible. Like we can take different T, different H. By the many combinations of D and H, we can get the 520 centimeter cube. But we have to find out that's in that cylinder where the area should be minimum for the given volume. For that, what we will do, we will we will differentiate the area with respect to volume, or and we try to find out what is the minimum area. Okay, so we will differentiate this area with respect to the diameter, so that we could directly find out the relation between the volume and diameter. So we want to minimize the area so that we could increase the solidification time. For that, we want to differentiate. We are taking derivative of area with respect to diameter, and we are putting it to 0 to in order to find out the minimum. So if we do that, we will get the relation 4v by d square plus pi d is equals to 0, or what we can say, d cube is equals to 4v by pi. Okay, now we have got some relation between the diameter and the volume of the riser, but if you see, what is the relation between the volume and the height which we had earlier? Okay, here if we substitute back v with the uh, if we want to substitute the volume with the h or the height, because ultimately what we want relation between the diameter and height, and volume is the fix. But if we substitute the volume with the earlier values, that v is equal to pi by 4 d square h, or from here if we substitute the volume and we try to find out, what we will get, d square h is equals to d cube, or h is equals to t. So for the given volume, if you want to find out what is the minimum area of cylinder which is possible, so this kind of relation we should have, height should be equal to the diameter. So this condition, it has to satisfy to minimize the surface area. Now let's try to find out. Now let's try to find out the what should be the d and h for the given volume of the riser. Okay, if you have gone through the lecture, then it is recommended that the volume of riser should be volume of riser, it should be 3 times of shrinkage volume. So this is the practical thing. I mean, if this much of volume of riser should be there in the terms of shrinkage volume. So already we have calculated the shrinkage volume. So that was 3 times of, if you see what was the volume, 520 centimeter cube, 520 centimeter cube, or what we will get, 1560 centimeter cube. So this much volume we want. So that should be the volume of the riser we are looking for. And now if we use the relationship which we have got, that the height and d, they are the same, and if we try to calculate it, that should be come out 4 times of volume of riser power 1 by 3. So it is just an inverse relation what we have choose with what we have used for the uh, find out the volume. So if you write like this, pi by 4 t square h, and if you substitute, since h and d are equal, so we all should be the pi by 4 d cube. So if you try to calculate 3, so this relation will come, and now we know the volume of riser, and we will substitute that value here. So h will be equals to 4 into 1560 pi 3.14 raised to the power 1 by 3. To try to find out what is there, that is 7.920 centimeter. So whatever knowledge we have utilized, we have trying to find out the some fix. We have trying to find out what is the volume shrinkage. From volume shrinkage, we arrive to the what is the riser volume which is needed, and from that volume we try to find out what is the minimum surface area, what is the diameter of the cylinder with minimum surface area. So diameter as well as the height comes out to be this much, 7.920 centimeter. Okay, but it is not sufficient. Why? Till now we haven't calculated whether our casting will solidify first or our riser will solidify first. Okay, so uh, first of all we will calculate uh, which will we will try to find out the ratio, area by volume ratio, for casting and area by volume ratio of riser. Okay, so we need to find out these two ratio, and we have to check whether which ratio is higher. We want what we want the a by v ratio of casting should be greater than the a by v ratio of riser. Okay, so that our riser should solidify later but our casting should solidify first. Okay, if opposite will happen, then our riser will not serve the purpose. So for let's try to calculate for the riser. So a by v of riser, it will comes out to be, if you calculate it, it will directly come out to be 6 by d or 6 by h. And if you substitute the value, what we will get, 6 divided by 7.920 centimeter inverse, or 0.75 centimeter inverse. Now we will try to find out what is the a by v ratio for casting. If we try to calculate it, then what we will get, 6 times 20, 620 into 20 divided by 20 cube. That comes out to be 0.3 centimeter inverse. Okay. Okay, I need to add one more slide. Wait. Okay. Okay. So right now what we have got? We have got A by V of a riser is equal to 0.75 centimeter inverse, whereas the A by, A by V of casting 0.3 centimeter inverse. So, or we can say A by V of riser is, it is greater than A by V of casting. So if this is the case, then what will happen? Our riser will solidify earlier, whereas our casting will solidify later. So it means whatever dimensions or design we have got, it will not work, because our riser will already get solidified. It will not able to supply the metal to the casting. So then we have to apply another condition. So keeping the ratio a by a is keeping the ratio same, that height is equals to d, this this condition we will keep parallelly. We will apply this condition also. We will try to calculate the new dimensions of the riser, which will satisfy these two conditions. Yes, which condition? Area of A by B of riser, it should be either less or it should be equals to the area by volume of casting. So we right now we are trying to find out the new dimensions which should satisfy h is equal to d, as well as this condition. A by V ratio of riser should be less than or equal to A by V ratio of casting, so that our riser should not get solidified earlier than the our casting. So if you calculate this, what we will get? 6 by D should be less than A by V ratio of casting is 0.3, or what we can say, this should be greater than or equals to 6 divided by 0.3, or we can say D should be greater than 20 centimeter. Since D is equal to H, so H should be, D and H both should be greater, H should also be greater than 20, or here H should also be greater than or equal to 20. Okay, so the correct answer for this problem is A. Okay, so is it clear to everyone, or still any of you have doubt? Is it clear to everyone? Please, can you please give your response in the chat? If you have any confusion in any step, please ask me. Okay. Okay, if it's clear to everyone, now let's quickly move to the last problem of the day. Please read it and try to give your response in the chat box. Okay, yes, I have got from the Nagasri Nivas. Others? Okay, okay. What I will do, I will quickly explain what is the Kn relationship and which assumptions are involved in the Keynes relationship and where it is useful. So, uh, till now, whatever we have seen that the solidification time, uh, it was proportional to the square, this square of the volume by area ratio or the volume by surface area ratio. But in Keynes relationship, the assumption has been taken and a curve has been plotted in order to find out what is the whether the casting is sound or not. So so the curve is something like that, and here I am showing its x-axis and y-axis. Here on the y-axis we have uh, a term called freezing ratio, which is defined as a by v of casting divided by a by v of riser, and on the y-axis what has been shown, it is called volume ratio, which is given by volume of riser divided by volume of casting. So these two plots has been shown and a curve is drawn, and the equation of this curve is x is equals to a divided by y minus p plus c. So what is x here? X is nothing, it is the volume ratio, whereas the y, x is the volume ratio and y is the freezing ratio. A is the freezing constant for the metal. It is a material property, freezing constant. And B is the contraction ratio from liquid to solid. Contraction ratio. And C is the basically C is also a constant, but it depends on the what kind of medium our casting is surrounded. So it is also a constant which depends on the uh, media around the riser and the casting. Around the riser and casting. So this curve is drawn, and if 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 we design a casting whose which is coming in this zone or the right side of this curve, it means it has been found that our casting is sound, or it is having very less defect. So this zone is called sound casting. Whereas the if we have designed riser and a casting in such a way so that if it is coming in this zone, so this is the defective casting. Okay, so so this is curve, it is drawn for a given material. So typically uh, C is equals to 1 if we have same kind of material around, same kind of environment around the riser and the casting. And for steel, A is equals to 0.1 and B is equals to 0.3. So this curve help us to find out whether our casting is good, whatever designing we have make for given volume and for the given volume of the casting and the riser. So whether it is correct or not, whatever surface area we have taken, it is suitable for the sound casting or not. So but the assumption is that here the soliding time is proportional to the V by A, whereas the earlier cases we have taken the V by A to the square. So linear, so cooling rate is nearly proportional to the surface area to the volume. So that is the correct answer. But I have explained what is the application of this curve or the Keynes method. So it is used to find out whether our casting is good or it has some defects. So this was all for the today. So if any of you have any doubt, please let me know, or we shall end our session here for the today. Any doubts? Any question? Okay, if there is no doubts, it is clear to everyone. So we will end the session here, and we will meet next Tuesday at the same time with some new sets of problem based on the uh, next week or the fifth week lectures. Okay, if any of you have any feedback, you can tell me. Any suggestions? Okay, if there is no doubt, then good night to everyone. We will meet in the next week. Thank you so much.